Good morning to everybody. Welcome to the mass transfer course. Today will be lecture 12. Here we are discussing the convective mass transfer and mass transfer coefficients. In lecture 11, we discussed about the mass transfer coefficients and how to calculate the mass transfer coefficient using empirical correlations with dimensionless numbers. And why you use the empirical correlation? Because that day I told you the no accurate theories are available to calculate the mass transfer coefficients. I mentioned the word no accurate theories are available. That's why people use the empirical correlations and using dimensionless. Today we talk about the theories are available to calculate the mass transfer coefficient, and definitely which theories we will discuss. You will see these theories are not very good to calculate the accurate calculation of mass transfer coefficient, because there are certain assumptions they have taken, and which assumptions, because of this assumption, it did not have much practical or accurate availability of mass transfer coefficients. So, but people tried some theories, and that we will discuss, and there we will get some feelings how mass transfer coefficient is varying with delta, how mass transfer coefficient is varying with DAB. That some ideas we will get. So let's try to discuss these theories for the calculation of mass transfer coefficients. There are 4 theories are available. First one is film theory, second one is penetration theory, third one is surface renewal theory, and fourth one is boundary layer theory. Now, first one is film theory. What is film theory? Let's take, this is the soluble solid wall, and fluid is flowing over there. Okay, so at Z equal to delta, that's surface concentration, maximum concentration of solid will be CAI, and at the bulk, okay, at the bulk that will be CAB, and this will be your concentration profile, 2 concentration profile. Okay. So, and this is my boundary layer thickness. Now, developing this film theory, what they made few assumptions. What the assumptions? Mass transfer occurs by purely molecular diffusion through a stagnant fluid layer at the phase boundary. That means they are telling this is what this stagnant fluid is, that is purely molecular. You understand? The convective mass transfer for the molecular diffusion, we also calculated what will be the mass transfer coefficient, what it will be explained. That also we can calculate. But same assumption are there, but what correlation we use because of convective is, because we know because of the convective mass transfer coefficient, maximum mass transfer. If you, that's why if you put sugar cube into a glass of water, it takes half an hour to dissolve. That is molecular diffusion. But if you stir it, within 30 seconds it will be dissolved. So convective mass transfer going much faster than the molecular diffusion. But here that they are making this thing, they are calculating the mass transfer based on the molecular diffusion. So now you understand what will be its accuracy based on this theory. Second thing they are telling that if you see Na, what was our governing equation? Na equal to Na plus Nb Ca by C minus DAB dCA dZ. That was our governing, and this term was our convective or bulk term, and this was our molecular diffusion. But and we have seen for convective mass transfer the contribution of bulk term or convective term is much, but they are telling bulk term flow, that means this term is small, and flux can be written as, that means this is 0, Na equal to this. So bulk term they are considering this thing, and this will be applicable only when this is a, that is the molecular diffusion. So they are actually film theory is developed based on molecular diffusion, and if this is thin, actually then this will be the true concentration profile, and but with this assumption the concentration profile will be linear. That we'll see later. We'll see when we derive this. Now this is stagnant film. So let's take at z equal to 0, and this is z equal to delta. At z equal to z, NaZ, and at Na this point is at z plus delta z, that is Na plus z plus delta z, that is the flux. Okay. So if you take this rate of input of the solute at z, Na into z, output z plus delta z, Na z plus zeta, accumulation term equal to 0, and if you take this component balance, input rate of input minus rate of accumulation equal, this is equal to 0. Okay, rate of accumulation, why it is 0? Because it is under steady state. Now if you divide it by delta z, and if you take the limit delta z tends to 0, then this equation will come minus n dna dz equal to 0, or then dna dz equal to 0. This type of thing already we have seen in your heat transfer course in discussing in heat conduction. Okay, that was dt dz. In this case, dna dt. Now if I put Na equal to minus dAb dCA by dz, again I am telling I am neglecting the bulk term, that is the as per assumption. So if you put this one, so dna dz, then it will be dAb d2Ca dz square, this is equal to 0. This will be my governing equation. You in heat transfer also you have seen this type of thing in conduction, that was K d2T by dz square, here dAb d2Ca by dz square. Now if you integrate, if you make an integration, so solve this differential, so this dz equal to A1, then again Ca will be A1z plus A2. Now what is the boundary condition? At z equal to 0, Ca equal to Ci. So at z equal to 0, so this term will go, so A2 will be Ci, and z equal to delta, Ca will be Cab. So Cab, Ca will be Cab, A will be A, z equal to delta, and A2 already we have found Ci. So A1 equal to Cab minus Ci by delta. So now if we put this A1, A2 in this equation, Ca will be Ci minus Cab z plus z. So if you see, this is the linear relationship. Okay, Ci z. So that's why if you see here, this is the, according to this assumption, this will be your concentration profile, but actual concentration profile will be this. So that much error is there. Now what is Na? Na equal to minus dAb dCA dz at z equal to z, because you know whatever is at that at z equal to whatever this is, this will come. So I will integrate this limit, I will take at z equal to 0. Then if you put this one, dCA dz, Cai minus Cab, this term will go 1 by delta. So then Na will be dAb delta Cai minus Cab. So your KL equal to this. If you see, same expression already we got in molecular diffusion. If you can remember, KL equal to dA by delta. Okay. So this is the film theory, and it has very, this is good for, you know, for theory as a theory, but its accuracy is not good. Okay. Now penetration theory. Penetration theory, if we want to discuss this, let's take one example. Let's take air ammonia mixture is there. Okay, and I want to absorb ammonia from this mixture to within water. So what will be my arrangement? There will be a pool of water, okay, and we'll pass the air ammonia mixture from the bottom through a bubble. I will put some tube and bubble will come. So when bubble is at the bottom, it will rise, and when it will come to the top, then it will go. But when it will come from bottom to surface, upper surface, when it will travel this part, and that time ammonia will diffuse from this air bubble to water liquid, isn't it? So let's take this is on bubble, okay, air bubble, air inside the ammonia is there. So water when it is rising, water is touch, when water first it will touch air, when you touch there will be interface, then water will move along this periphery, and when it will come to the bottom, then it will detach. Then again another water layer will come. So this is the unsteady, with time it will form. Okay, so this is the this phenomenon is unsteady state. So unsteady state mass transfer occurs with liquid element so long as it is in contact with the bubble. But and when they will touch interface, there will be on equilibrium. Equilibrium exists at rest. And third assumption they are taking that each of the liquid elements stays in contact with the gas has the same period of time. So when it will on liquid element, when it is at the top it is touching, then it is coming down from there. When it is coming down, it is, and what is the how much time it is taking? So that is the contact time Tc equal to what is the bubble diameter dB, and UV is the rising velocity of the bubble. So that will be your contact time. Now for this, so to solve this type of problem, you need the unsteady state equation, and you have studied a fixed first law, that is J equal to minus DAB dCA by dZ, and fixed second law is this dCA dt equal to DAB d2CA by dZ square. Now if you see, if you want to solve on differential equation, you need the boundary conditions. And what are the orders? If there are second order, two boundary conditions are required. In this case, there are 3, 2 plus 1, 3. So you need a 3 boundary conditions. So what are the boundary conditions? First origin is initial. When t equal to 0, z equal to greater than equal to 0, means when the liquid element did not touch the bubble, then the Ca will be say what is the bulk concentration, that will be the concentration. But when t greater than equal to z equal to 0, then it is in equilibrium, so this will be surface concentration. Then again z equal to infinity, when it is mass transfer occur, okay, then it will come again, the concentration will be bulk concentration C. So these are the 3 boundary conditions, and this is my governing equation, differential equation, and you have studied engineering mathematics 3, where you have handled this type of thing, and the solution of this thing will be like this: Ca minus Cab divided by Ci minus Ca 1 minus ERF eta, error function. You have studied this one in mathematics, where eta equal to Z by 2 root over dAB T, where T is the contact time. Okay. Now what is at any contact in what will be flux? dAB minus dAB dCA dZ at Z equal to 0. Okay. So now if you take this dCA dZ in this error function, then this will come root over dAB by pi T Ca minus Ca. Okay. This is for any contact. But what will be the average flux? Average flux contact time will be 0 to Tc and 1 by Tc Na dt, okay, by 1 by Tc, and then it will be 2 root over dAB by Tc into Ci. So instantaneous mass transfer KL equal to this root over dAB by pi T. Okay, and average mass transfer coefficient KL average into 2 root over dAB by pi Tc. And keep it in mind, penetration theory is available when on the gas phase is bubbling in liquid. Okay, and here if you see KL average, K is proportional to direct root over dAB, but if you see in this case it was KL proportional to dAB, so there is some difference. Then third theory is surface renewal theory. Surface renewal theory is nothing but some modification of penetration theory. In penetration theory, one assumption was taken that each of the liquid elements stays in contact with the gas or the other phase for the same period. Means all the liquid have a same contact time with the gas, but practically it is not possible. There will be different bubble diameter and some other things will also come. Okay, it may detach. It is not always necessary to come here, then it may detach here also. So that probability, that things they have considered in surface renewal theory, and they put this scale average. They kept the dAB that is same. Here you can see dAB whatever same, but they put the instead of Tc S. S is the model parameter, that is fractional rate of surface renewal. Okay, that is the point parameter they have taken. With this, they have expressed this. Now, fourth thing is boundary layer. So, what is the boundary layer theory? Let's take, this is one flat plate with soluble coating. Okay, means, and fluid is flowing over this flat plate. So, if fluid is flowing, then there will be hydrodynamic boundary layer, that is delta X. Okay, and at the edge it will be 0, and when it will around the line it will increase, and after some time it will be 0. And when this velocity will be pristine velocity almost, then after this, so up to this is boundary layer you have studied in your fluid dynamics. Now as this plate is soluble coating, okay, so whatever the soluble thing is there, it will be dissolved in fluid. So, and it is the maximum concentration CI, and there will be bulk concentration. Okay, so there is a concentration driving force. So solute will dissolve from here to this, and here also that boundary layer will be there. It is delta M, that is for mass transfer. Now, in this case, if Smith number is greater than 1, Smith number means momentum diffusivity by mass diffusivity. Momentum greater than 1 means momentum diffusivity is higher than your mass diffusivity. So as momentum diffusivity has a better influence, so that this boundary layer will be higher than this mass boundary. If Smith number is less than 1, then concentration boundary or mass boundary will be higher, and this boundary will be lower. Similar thing already you have studied in your heat transfer. In that case you have studied the Prandtl number. Prandtl number was momentum diffusivity by thermal. If Prandtl number greater than 1 means your hydrodynamic boundary layer will be higher and your thermal boundary layer will be lower. If Prandtl number is less than unity, then your thermal boundary layer will higher and your momentum boundary layer will be lower. And with this boundary layer theory and taking the dimensionless numbers, and then finally that expression F root number equal to KLX x by DAB equal to this. Okay, where x is the local mass transfer at particular time, and if you take the average, KL average L by DAB, okay, then this equation will become 0.664 REL whole to the power of 2 power 1.3. Now here it is to be noted KL equal to Smith number nu by DAB to the 1/3. So DAB 1/3. This DAB, so actually KL is proportional to DAB to the 2/3. And among these four boundary layer theory, that boundary layer theory is the more accurate. Okay. So in summary, if you take this mass transfer theories of mass transfer and what are the coefficient, how Film theory, it was under steady state, KL was D by DAB by delta, so KL directly proportional to DAB, here model parameter is delta. Penetration theory, unsteady state, KL instantaneous equal to DAB by pi t whole to the power of KL average to DAB pi tc whole to the power of KL whole to the power of half, and this is the TC. Surface renewal theory, KL average equal to ds equal to the power of KL equal to directly equal to the power of this. Boundary layer theory, KL equal to d to the power 2. Here although we are discussing these theories and there are limitations, actually when in problem, when you will going to calculate this one, you have to calculate through accurate correlations, what we discussed in last lecture. However, these are important to make the qualitative sense as how KL, okay, mass transfer coefficient is varying with DAB or delta like this. It will help to develop the correlations. That's why these are the important things we discuss here. So thank you for your attention and have a nice time. Bye.